Today we will be looking at symmetries of quadrilaterals again. So this is day 2 on lesson 6.6, and we are going to continue on with the same objective we had before, which is given a quadrilateral, a four-sided polygon, I can list its symmetries, both rotational and reflectional, in 2 out of 2 problems. So let's review, what does symmetry mean in geometry? We had sort of informal descriptions of it. We talked about things like mirroring, things looked the same, or maybe they looked opposite. You think of how things look in a mirror, how they're opposite. We might even draw a picture, like we had an example of a butterfly. A butterfly is an example of a reflectional symmetry. You can see if we have that line in the middle, it looks the same on both sides. But then we also have this idea of rotational symmetry, an idea that we could spin something around and it would look the same. So for instance, maybe a flower would be like a rotational symmetry. So if we spun that around, the petals would land on the next petal. This petal would land on this petal would land on this petal, and we would get the same thing back. So in general, symmetry in geometry means we've moved something, or the official term we use is transform. We've transformed something, a transformation that maps onto itself. So we perform a transformation, something like a reflection or a rotation, and we get the exact same thing back. We get this butterfly back when we reflect it over that line. We get this flower back when we rotate it around either direction. So today we're going to talk specifically about symmetries of certain kinds of quadrilaterals. And this may look familiar. We talked about this hierarchy a little bit. We started with quadrilaterals at the top, a polygon with 4 sides, and we divided that by how many pairs of parallel lines they have. If they have exactly 1 pair, that is called a trapezoid. If it has 2 pairs, we call it a parallelogram. And remember, there is actually another one that has 0 pairs of parallel sides. We're just not talking about that particular quadrilateral today. Parallelograms can be further divided into 2 categories: rhombuses, which have 4 congruent sides, meaning they're all the same length, and rectangles, which have 4 right angles. Rhombuses are parallelograms, and rectangles are also parallelograms. They're particular kinds of parallelograms. Then if we combine rhombuses and rectangles, we get squares. Squares have 4 congruent sides, that makes them a rhombus, and 4 right angles, that makes them a rectangle. So squares are considered both rhombuses and rectangles. All 3 of these are considered parallelograms, and all of these down here are considered quadrilaterals. So we're going to look at those specific shapes today and determine what their lines of reflectional symmetry are and what their rotational symmetry is. So the first one we're going to look at is one we are actually reviewing from yesterday. We already looked at the symmetries of a square, but just for a quick review, we're going to determine how many lines of symmetry and which angles of symmetrical rotation are there for a square. So here are all the features of a square. It's 4 sides, so it's a quadrilateral. 2 pairs of parallel sides means it's a parallelogram. 4 right angles makes it a rectangle, and 4 congruent sides makes it a rhombus, and a rectangle and a rhombus combined make a square. So how many lines of symmetry are there? How do we figure out lines of symmetry? Well, we can think of these as folding lines, and you can see over here I've got this piece of paper that's a square on the video, and we're actually going to attempt to fold this. Now, we're very accustomed to squares. We've seen a lot of reflections of squares all our lives. But it's going to be important to do this with paper or with some other manipulative for the other shapes, because they can be a little bit misleading. So we're going to work with the square first. Try to find the lines of reflectional symmetry. So I'm going to try folding this in half first. This is how we often fold squares. We try to match up the edges and then fold it kind of right in the middle. And you can see if I had gotten that perfectly folded, we wouldn't have any sides hanging over, we wouldn't have any corners hanging over. It does a little bit, but just because I didn't fold it perfectly. That is a line of reflectional symmetry for a square. Similarly, I can fold it half this way, fold it in half this side over to this side. And again, it matches with no side hanging over, no corners out of the way. So that is another line of reflectional symmetry. So we had this one, the horizontal, what we call the horizontal bisector. We also had this one, which we call the vertical bisector. Now another option we are going to want to try on these are diagonals. We want to see if the diagonals are lines of symmetry. So we're going to fold from corner to corner now. Doing math origami today. Corner to corner. Notice, again, I didn't fold this perfectly, but if I had, we would have, that was better. We have no corners hanging over, no sides hanging over. Flip it over. See, that's a diagonal symmetry worked. Okay, so let's try the other diagonal now. Fold this over along the diagonal. And look, that one matched as well. So diagonal symmetry worked. So overall in a square, we got 1, 2, 3, 4 lines of symmetry. Now we could try other ones, but we have sort of a sense that they're not going to work because they need to be equal on both sides. So if we fold it in a not middle place, we're pretty sure it's going to hang over the side. Or maybe if we fold it along a non-vertical, non-horizontal line, so a diagonal type line that isn't between the corners, we have a pretty good sense that's not going to be even, going to match evenly. So those seem to be our only lines of reflection. Now to do angles of rotation, we can put this on a piece of paper. And I'll just draw an outline of this right here so we can tell where it started. So you can see we have that outline of a square. And we're going to just rotate this. Now remember, if I rotate it 360 degrees, that will be all the way around. So I'm going to rotate it until it matches up, until we don't have any corners hanging off, any edges hanging off. So rotate it, and I get, there, 90 degrees. That's a square. You can tell that's 90 degrees because the top is now on the side. So 90 degrees is one of our angles of rotation. There's one. 180 degrees is an angle of rotation. There's another one, 270. And we're back to the beginning. 360 is a valid angle of rotation. We just call it trivial because everything is going to map onto itself when you rotate it 360 degrees because that's a full circle. Everything gets back to where it was. So we call that trivial, we don't count it. So if we're going to list our lines of symmetry now, we said there are 4. So there are 4, and they were 2 diagonals, and then 2 bisectors, bisectors of opposite sides. That meant we cut them down the middle. This is a bisector, this is a bisector. And over here, this is a bisector, and this is a bisector. Is this the same for all squares or just this one? What do you think? So I think if we scale a square, all squares are going to be similar. We can make a square bigger, we can make it smaller, but if we draw a diagonal, these sides are all going to be the same, which means when we fold them over, they will match. And all of these angles are right angles, So when we fold those over, those are going to match too. So no matter how big our square is, those features of a square are all there. So this is the same for all squares. Same for all squares. Because the sides are all congruent and the angles are congruent. So sides are congruent, remember the symbol, congruent, and angles are all congruent. All right, and then rotational symmetry, we said there were three, right? We said there was 90, 180, and 270. And is this the same for all squares? Yeah, it sure is, for the same reasons. When we rotate this side over here, well, these sides are the same, so they're always going to be the same. As is that side, as is that side. So no matter how big the square is, these sides will all map onto themselves. All right, so let's take a look now that we reviewed how to do this, let's take a quick look at a rectangle. Let's see if we can figure out the lines of symmetry for a rectangle. So we need a rectangle. We're going to attempt to fold this in half. This way. Looks like it matches. And maybe we'll attempt to fold it in half the other way. Rectangles we are also very familiar with. We've been folding pieces of paper probably since we were very small. So we know that those are lines of symmetry, the bisectors, horizontal and vertical bisectors. But what about the diagonals? Do you think the diagonals will be for a rectangle? Let's find out. See, I need to fold from this corner to this corner. I didn't quite get that perfect. There we go. That doesn't seem to match. That's got a lot hanging over, two corners hanging off the edge. What about this diagonal? We fold it along that diagonal. What do we get? Well, I'd need to fold it a little closer to the corners, but still, it looks like we're going to have corners hanging off the edge. Diagonals are not lines of reflection for a rectangle. The only lines of reflection for a rectangle are the horizontal and vertical bisectors. So let's record that. There are only two lines of symmetry for a rectangle, and they are the horizontal and vertical bisectors. And in just a second, we'll come back to this question. Let's look at our rotational symmetries first. And instead of doing that on the video, I'm actually just going to do this up here. Because we can do this in our little presentation here. And I can just grab this and rotate it around, and you can see here we are at 90 degrees. That definitely doesn't match up. Keep going. We get to, there, 180. That does match up. Not match, no 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 match. No, 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 no. And we are back to 360. We're back to this at the top. So there was only one angle of rotational symmetry, and it was 180. So now, are these lines of symmetry the same for all rectangles, or just this one? Same with symmetrical angles of rotation. Are they the same, or are there exceptions? Well, let's reason this. Let's see. These sides have to be the same length because it's a parallelogram, and these sides have to be the same length. These are symbols we use for congruence. So like one tick mark means these are congruent to each other, same length. Two tick marks means these are the same length as each other, but not the same as this one. And we know in a rectangle, all four angles are going to be right angles. They're all going to be the same. So if we rotate this 90 degrees, we know that this side becomes this side. And those are not necessarily the same. Could they be the same? In a rectangle, is it possible for this side to be, instead of 2, is it possible for that side to be the same? Well, let's see, we have 4 sides, 2 pairs of parallel sides, and 4 right angles. Oh. We tend to think of rectangles as having one longer side, but that's not actually specified in our requirements. All we said is 4 right angles. And remember, we also said that squares are rectangles. If a square is a rectangle, then it is possible for this side to be the same, and then it'll rotate on. And those will be the same. But if we're not dealing with a square, if we're dealing with a rectangle that looks like this, that is not a square, this side will not match that side. However, when we get all the way around to 180, those will have to match because by definition, they're the same length, by the definition of a parallelogram. Similarly, when we get to 270, if this were a square rectangle, these sides would match, but not for an oblong rectangle like this one. And then, of course, back to 360, they all figures map onto themselves at 360. So all of them, that was actually, we were just talking about rotational, weren't we? So all rectangles have 180. Squares, though, also have 90 and 270. So there are some exceptions, but all rectangles will have rotational symmetry at least at 180. What about the reflectional now? If we reflect here and we reflect here. Well, we said that these are bisectors, right? They're going to cut these in half, so this is going to be the same distance as this. But the whole length is the same as well, so those would have to be the same down here also. That means the whole thing, if we cut this whole thing in half this way, this length is the same, that length is the same, this length is the same, this length is the same, this length is the same based on the definition of the rectangle, and all 4 of these corners are the same. So we can show that any rectangle, regardless of the size, is going to be cut in half. This is going to be a line of symmetry for any rectangle. And we can use a similar argument for this line. Now what about the diagonals? We said the diagonal wasn't in this case. This is a nope line. But what about squares? We said that squares had diagonal lines of symmetry. So if we have a square rectangle, again, this is going to be an exception. So all rectangles have the two bisector lines of reflection. Squares also have diagonals. Interesting. Okay, so let's check out parallelograms now. Parallelogram was higher up on our hierarchy. Let me grab my paper. There's a parallelogram. Our definition says we have 4 sides and 2 pairs of parallel sides. Let's try some folding here. Let's fold a parallelogram. All right, so we like to fold it in half, top to bottom usually. Let's try that. Oh, that looks like it has a hanging off part. If I turn it over, a hanging off part over here too. So that didn't seem to work. Let's try halfway this way. Let's see. That didn't seem to work either. What if I do it more at like an angle that kind of matches this angle? Maybe I can try that. Fold it at an angle like that. That doesn't seem to work. Maybe the diagonals? Let's try the diagonals. More hangy-offy bits. Let's try the other diagonal. This way. More non-matching bits. I couldn't find any lines of symmetry for the parallelogram. Can you? Are there any other places we could fold this? Like, I can't see any. I can't think of any. I'm going to say this is 0. I don't think we have any lines of symmetry. So, list them. There's nothing to list, right? There's 0. Is this the same for all parallelograms? We'll come back to this. We'll come back to this question. Let's look at rotational symmetry first. So I'm going to do this up on the board as well. So here we go. We're going to try to rotate this around. We get to 90 degrees, and that definitely doesn't match. We keep rotating, keep rotating, keep rotating. Oh, look. That one does match. So 180. Looks like 180 is one. Keep going, keep going. No, we get to 270. That definitely doesn't match. And we're back to 360, which always is a trivial angle of rotation. So let's see. We said there was only one, and it was 180. That was like rectangles, right? Rectangles only had one, and it was 180. So are these the same for all parallelograms? Can you construct an argument based on lengths of sides for why this would or wouldn't be true of all parallelograms? Remember, these sides are going to be the same length. These sides are going to be the same length. These aren't necessarily right angles, right? Only for rectangles it would be, but we can say that these two are the same. And these two are also the same. So if we rotate this all the way around, this side will match this side. This angle will come up and match this angle. So you can see 180 has to work for all parallelograms because of the definition of a parallelogram. But would some parallelograms have more angles of rotation? For instance, we look back at our hierarchy here, we said rectangles, which we just looked at, are parallelograms. And squares are parallelograms. We said squares have 3 angles of rotation. So again, squares are going to be an exception here. All parallelograms will have 180, but squares also have 270 and 90. So all parallelograms will have 180. Squares also have 90 and 270. And the y here is because of the definition of a parallelogram, the way it's set up, with opposite sides being congruent and opposite sides here being congruent. Now, how many lines of symmetry are there? We said there were none. Is this the same for all parallelograms? We just looked at 2 instances, rectangles and squares, where that wasn't true, so this is definitely not true. No. Squares and rectangles have more than 0. But will this be true of any parallelogram that is not a square or rectangle? We might not have enough information for that yet. Let's hold out. Let's move on to a rhombus. How many lines of symmetry do we have for a rhombus? Let's check that out. Try to fold a rhombus. Well, we like to fold it in half. Fold the top down to the bottom and see if we get a line of symmetry there. Hey, that one did work. Look at that. It folded down. And what if we do it the other way? Fold it in half, left to right. Yeah, that one also worked. Awesome. We did find some symmetries there. Now, let's look at this actually, because those are diagonals where we just folded it vertex to vertex, right? So we're just kind of looking at this sideways. Maybe we can fold it in half along these bisectors. Let's try that. So fold this side over to this side. Oh, I see hangy-offy bits over here. Darn. How about this way? This side over to this side. More hangy-offy bits. Nope, those didn't reflect evenly. Is there anywhere else we could? So that was the bisector, that was the bisector. If we tried anywhere that wasn't a bisector, we know that wouldn't because it's not in the middle. I think that might be all of them. I think it might be just this one and that one. So how many lines of symmetry are there? Well, we said there are 2. There are 2, and we said it's both diagonals this time. We'll come back to this question. Rotational symmetry now. Well, let's take a look. If we rotate this 90 degrees, oh look, that didn't match up. Let's rotate it another 90 degrees. So we're at 180. Oh look, the 180 matched up. So another 90 degrees, that's, oh no, that doesn't match. 270 doesn't work. And another 90 degrees we get here. So we say there was one. There was just one, and it was 180. That sounds exactly like rectangles and parallelograms. We said both of those only had 180. Now, let's look at the features of a rhombus. We're getting used to this, right? 4 sides, 2 pairs of parallel sides. These are parallel. And 4 congruent sides. So all of these have the same measure. The things that are different, though, might be the angles. The angles are not necessarily all the same because that's only when they're rectangles, right? So this one might be the same. Well, that one definitely is the same as that one. And this one is the same as this one. Those are features of parallel lines, parallel intersections. But all 4 sides are the same by the definition of a rhombus. So if we rotate this 180 degrees, well, if we rotate it 90 degrees, so we rotate basically this corner onto this corner and this side onto this side, the sides will be similar lengths, but the angles are going to be different. So the sides aren't actually going to match up because the angles, this angle is not the same as that angle, will go 90 degrees. However, if we go all the way around 180 degrees, this angle now matches this angle. Similarly, this line, this side is going to match this side. They're the same length. This side's going to match this side, and that side, and that side. So all 4 sides will match each other. These 2 angles will pair up. And so yeah, all rhombuses are going to have 180. But again, we have those exceptions, right? We said a square is an example of a rhombus, which has more. So yes, all rhombuses have 180, but squares also have 90 and 270. Now, do all rhombuses have the same lines of symmetry? We said those are both diagonals here. Oops, let's actually draw that in the middle. There we go. So if we think about how these diagonals work, they're going to split these angles in half. So we could even have like a smaller angle right here that's the same. And you can see those angles are going to match, those angles are going to match, these sides are going to match, these sides match. And similarly, these two are split in half, these two, so these are going to match as well. So all of these pieces are the same on both sides, and we didn't specify anything about the size of this rhombus. Any size rhombus is going to have those features. So for the same reason, splitting it this way is going to work as well. Both diagonals will always be lines of symmetry for a rhombus. But again, good old square being our exception, squares have 4 lines of symmetry. So all rhombuses have 2 diagonals as lines of symmetry, but squares also have the bisectors. Neat. Okay, let's look at trapezoids. Anything surprising yet? Anything you didn't expect? Let's try to find some reflectional symmetry for isosceles trapezoids. So we like to fold the top down to meet the bottom. Let's see if we have any hanging offy sides. Oh yes, we do. We have 2 hanging offy sides. That doesn't look symmetrical. How about if we go left to right? We fold this side over to this side. How does that look? That looks like it matched. Yeah, that's a line of symmetry. Let me just trace that one so we know that it is. Okay, so we have a line of symmetry there. How about if we go corner to corner? That definitely has hanging offy bits. Let's try the other corner. Yep, also has hanging offy bits. Are there any other that would make sense? Anything that wasn't in the middle wouldn't make sense. I can't think of any others. So really maybe just that one. Just one line of reflection. So we said one line of reflective symmetry, and we said it was that vertical bisector of opposite sides. Remember, we're talking about middle here, and we draw a line through them. We'll come back to this question. Let's see if we can rotate it onto itself. Here we go. All right, so here we are at 90, nope. Here we are at 180, nope. Here we are at 270, nope. And here we are at 360, which is trivial. We said that one doesn't work. So actually we didn't run into any until 360. There are none. No angles of symmetrical rotation, and this is a nope because you can't list 0 items. Is this the same for all isosceles trapezoids? Remember, the definition of an isosceles trapezoid says that this side is the same length as this side. But trapezoids, we said, have exactly one pair of parallel sides. We know that these are not parallel, only these two are parallel. Which actually tells us that this side is a different length than this side. If they were parallel, or if these two were parallel, then these two would be the same length. We know that they're not. We know that those aren't parallel, so these two can't be the same length. We know they're different lengths. So if we were now to rotate this around, this side doesn't have a buddy. There's no other side on this trapezoid that's the same length as this one. So if we rotated this side, it wouldn't match. Down here, it wouldn't match. Over here, it wouldn't match. There's no way for this guy to go for him to match in a rotation. So yeah, this seems true for all isosceles trapezoids. It doesn't matter how big or how small the trapezoid is. This top piece will never have a match. This is true for all of them. And that's, again, because of the definition of an isosceles trapezoid. Okay, how about the bisector? Is the bisector always reflectional symmetry? let's think. If we divide this in two, then both of these sides will be the same. This side will be the same as this side. We call those A. And then this side won't be A, but it'll be the same as this side. This side will be the same. So if all three of these sides are the same, we also know that these angles will actually be the same. These angles will be the same, and these angles will be the same. All of those pieces tell us that, yeah, those are the same. So if we fold it there, it's going to match. So yeah, regardless of the size of the isosceles trapezoid rather, all of those will be the same. Now our last one we're going to look at, this scalene trapezoid, is a little bit interesting. It doesn't really have, it only has one pair of parallel lines, but it doesn't have any sides that are congruent. So let's take a look at folding this scalene trapezoid and see if we have any lines of symmetry. Fold the top to the bottom. Nope, doesn't look like it. Fold side to side. Like, I can't even imagine where exactly I'd fold this, maybe to try to get it to line up. That looks like it has stuff hanging over. Let's see, let's try angle to angle, or diagonal rather, corner to corner. That didn't work at all. Corner to corner on this one. Let's see. Let's go that way. That one looked like it came close, but if I flip it over, you can see, oh, there's actually a lot of hanging over on that side. So, scalene trapezoids seem to not have much going for them in terms of reflectional symmetry. I'm going to say that looks like it had none. I couldn't find any. This is a nope. We'll come back to this question. And let's try to rotate the scalene trapezoid now. Let's see, there's 90, 180, 270, no match until we get back to the beginning. So once again, this is none and nope. You can't list 0 members. So is this the same for all scalene trapezoids? Let's see, let's look at our definition. 4 sides, exactly one pair of parallel sides, so these 2 sides are parallel. The other 2 sides are not congruent, so we could say this one is not congruent to this one. Now, is it possible for these 2 sides to be congruent even though those 2 sides are not? It's kind of a question to consider. If these 2 lines are parallel and these 2 lines are not congruent, is it possible for these 2 sides to be congruent? So if we extend this out, these out to be the same length, then I would propose that these sides would either need to be, these sides are going to have to be parallel as well. They either need to be parallel or the same length. Maybe I can leave that up to you to justify to yourself. You can try to construct it, figure out why. But if that's the case, then we can also guarantee that this one is different from this one, which means none of these have buddies. None of these have buddies, which means if we try to rotate them, they're never going to match until they get back to themselves. So yeah, same. This is the same for all the scalene trapezoids because of the definition of a scalene trapezoid. How about rotation or reflectional symmetry? We cut it in half, we cut it in half there. Similar arguments. If we cut any of these in half, it's not going to match half of any of the others. And if we make it so that half does match where we do cut it, the other side won't match. So yeah, these reflectional lines of symmetry don't exist for any scalene trapezoid for the same reason, because the definition of a scalene trapezoid. So we can summarize everything we discovered here. The number of lines of symmetry are listed here, and the angles of symmetrical rotation are here. And you'll notice as we move down this hierarchy, remember rhombuses and rectangles are types of parallelograms, we add features. So, or another way to think of it is that we inherit them from the thing above us. So rectangles, parallelograms have a 180-degree rotation, which means both rhombuses and rectangles do too. But since square is a rhombus and a rectangle, it also has 180 degrees, and it's also got this 90-270 thing that it added. Squares get additional features. So parallelograms have no guaranteed lines of symmetry, but rectangles will always reflect over two bisectors, and rhombuses will always reflect over the two diagonals. Since squares are both rectangles and rhombuses, they inherit both of those features. Both bisectors and both diagonals are reflectional lines of symmetry. And then we have isosceles trapezoids and vertical trapezoids, or scalene trapezoids, that have their own features that aren't really in this hierarchy that we talked about. There's our big long summary of the symmetries of quadrilaterals. Kind of a massive lesson today, but hopefully it's a little bit fun. You get to fold things. So that covers today's objective. Given a quadrilateral, I can list its symmetries, both rotational and reflectional, in 2 out of 2 problems.